Hi students, in this video we'll discuss Turing machine, the definition of Turing machine, instantaneous description and the languages accepted by Turing machine. Turing machine, it is invented by Alan Turing in 1936. He is a British mathematician and he invented this Turing machine during the Second World War. It is a simple mathematical model of a general purpose computer. That is, it can perform any calculations that can be done by a computing device. Coming to this language hierarchy, you know about this language hierarchy. The innermost circle is the regular language, which is accepted by my finite automata. Next is context-free language, which is accepted by push-down automata. Then what about these type of language? To accept these type of language, I need the Turing machine. Languages accepted by Turing machine is recursive enumerable language. Coming to the definition of Turing machine, it is a 7-tuple machine. First tuple is Q, finite number of state, sigma, input alphabet, gamma, tape symbol, and next is delta, transition function, initial state of your Turing machine, and I have blank symbols in my Turing machine, and at last it is final states. And this Turing machine has 3 components. It has a tape, read-write head, and control unit. Tape. Tape, it is of infinite in length and it is divided into small cells. Each cell can hold a single character. Right. So no boundaries for my tape as it is infinite in length. And this cells of the tape is pointed by a read-write head. This read-write head can move in either direction. It can move in left or right direction. The head at each time step, it can read a data from the cell or it can write into the cell. And after doing read or write, it can move in either direction, either left or right. Here's an example. Here, this is the initial configuration. Read write head is pointing to the data A. It reads the data A and then this A is replaced with K, that is it has written K into that cell and then the read write head moves to left direction. Reading A, replacing A with K, right operation, then read write head moves in left direction. Right, that's what it is given. Reads A, writes K, moves left. And coming to this input string, when I place the input string in my tape, right, it should have blank symbols in both beginning and at the end. So these are the blank symbols. I have to keep these blank symbols in the beginning of my input string and at the end of my input string. These are the states and transitions. The meaning of this transition is Q1 state. When it reads A input, there is a change to Q2 and this A is replaced with B and the read-write head moves in left direction. After this operation, the read-write head moves in left direction. Similarly here, Q1 state, when it reads A input, there is a transition to Q2 and A is replaced with B and the read-write head moves in right direction. So, in Turing machine transitions, I have to specify these 3 things. From which state there is a transition to which state. I have to specify the state and the operation I have to specify and the direction of the read-write head. All these 3 things I have to specify in the transition of my Turing machine. Coming to the next one, Turing machines are deterministic. You know the meaning of deterministic. What do you mean by deterministic? When a state reads the input, there will be a transition to only one state. It cannot make a move to more than one state. See here, Q1 state, when it reads A input, there is a transition to Q2 and this is the operation. A is replaced with B and on the direction of your read write head. For input A, there is a transition to only one state. Similarly, Q1 state, when it reads B input, there is a transition to Q3. This is determinism. Check this, Q1 state, when it reads A input, there is a transition to two different states. Check both. Here also Q1 is reading A, here also Q1 is reading A. Right, for the same input A, it makes move to more than one state. So this is not determinism, it is non-determinism. Right, Turing machines are deterministic. Such type of transition, non-determinism, it is not allowed in Turing machine. And here partial transition function. You look at this input string A, B, A, C. Right. So here no transition for input symbol C. Q1 when it takes A, this A is replaced with B, transition to Q2 and the direction of your read write head is right. Similarly for B input I have specified the transition. But it is not needed. I have to specify the transition for all the input symbol. If you want, you can miss one or two input symbol transition. That is possible with Turing machine transition function. Acceptance. When in Turing machine, there is a condition. My Turing machine, it should halt. Right, I give an input to my Turing machine. It can recognize that input. It can say whether the input is a valid one or invalid one. If it is a valid one, as you all know, it will reach the final state. And here in my Turing machine, my machine should halt. Right, so if it is a valid input, machine halts in final state. Only if it is a valid one, machine will reach final state and it should halt. Right. If it is an invalid one, right, my machine can halt or sometimes my machine it will enter into an infinite loop. What happens when the machine enters into an infinite loop? If it enters into an infinite loop, it cannot reach your final state. It cannot reach your final state. Entering into infinite loop, the machine will never halt and the input is not accepted. Right, since it cannot reach your final state, input cannot be accepted. This happens when the machine enters into an infinite loop. Next, coming to the instantaneous description of your Turing machine, assume this is the current state of your Turing machine. Currently, my read write head, it is pointing to the cell B and the state is Q1. How to write the instantaneous description, right? How to write before this, you pick and write the symbols that is present before your read write head. Before your read write head, you have C and A. So first you write CA, then write the current state. Current state is Q1 and then write the symbols that is pointed by your read write head and the following symbols. So it will be BA. I'll tell you once again. First you have to write this symbols present before your read write head. Symbols present before your read write head. Then your current state and the symbol which is pointed by your read write head and the following symbols. CA, Q1, BA. One more example we can see how to write the instantaneous description. What is instantaneous description? Current state of your Turing machine. Currently, what is the state? And the read write head is pointing to which cell. Current state of your Turing machine is the instantaneous description of your Turing machine. One more example. Right, my read write head, it is pointing to X and this state is Q2. You check before your read write head, do you have any input symbols? No, you have only blank symbols. So you can start with Since no input symbol before my read write head, I'll start with Q2, then write the symbol which is pointed by read write head. Read write head is pointing to X and the remaining symbols you have to write. So your ID is Q2, Q2 X A Y B, Q2 X A Y B. This is one more example. My read write head is pointing to the symbol A. How to write the ID of your Turing machine? Check the symbol before read write head. Before read write head, you have X. So start with X. First you can write X, then the state Q0, and then write the symbol which is pointed by your read write head. It is A. And next is the remaining symbols Y, B. This is how you are supposed to write the instantaneous description. Next we can see recursive enumerable and recursive language. What is recursive enumerable language? The language accepted by any Turing machine is recursive enumerable language. Language is recursively enumerable if some Turing machine accepts it. Check out this. Let L be a recursively enumerable language and M is the Turing machine that accepts it. You can take a string that belongs to L. Since this string belongs to this language, definitely it will reach your final state. And you know my Turing machine, it should halt. So machine halts in final state. If W does not belong to the language L, right, there are two possibilities. Definitely my it will be in your non-final state. My Turing machine, it will be in your non-final state. It cannot reach your final state since it is a invalid input. Moreover, my Turing machine, either it will halt or it will enter into an infinite loop. Right, either it halts in a non-final state or loops forever. It enters into an infinite loop. So recursively enumerable language doesn't know how to handle invalid input. If I give an invalid input, it will enter into a loop. Right, but there is a language, recursive language. Recursive language is also accepted by Turing machine, but this language knows how to handle the invalid input. If I give, check out this, let L be a recursive language and M the Turing machine that accepts it. For a string W, if W belongs to L, my Turing machine, it halts in final state. If W does not belong to L, it halts in a non-final state. In both the cases, machine will halt. It won't enter into infinite loop in which language? Recursive language. Thank you, students.